All right, so let's start. I don't want to waste too much time. I was told I have way less time than I thought, so I will try to skip a few things. So today we are talking about Python. I named it the missing Python introduction for scientists. I will do a quick intro of myself. So my name is Tamás, as Georg already introduced me. I was born in Hungary in 1985, and I'm an astroparticle physicist at the Erlangen Center for Astroparticle Physics. And I'm working on the KN3-net neutrino experiment. I'm also a sysadmin, and I'm doing a lot of DevOps at ECAP, including the IT for ECAP and KN3-net and other experiments. And my programming background is I started around 1993 or so with Amiga Basic and tons of Go-tos, wrote my first toilet manager. It was a lot of fun. Nowadays, I do mostly Julia, Python, and Rust, JavaScript, C and C++ for work, Haskell for fun. Also learned a lot of other languages, and I'm working with Python since 1998. At the beginning, mainly to replace Perl and shell stuff for system administration, later also for science. I'm a Vim user if you're curious, but I switched to Emacs in 2020 in the Evo mode because it's the better software. And I like, so this is my desk in 2003. I like writing adventure motorcycles and building DIY synthesizers. So if you want to talk about that, I'm free. Okay, a tiny disclaimer. Let me move this one somewhere else. So this talk contains a lot of oversimplifications and blatant omissions due to time constraints. So we keep this in mind. Okay, let's talk about Python. So what is Python? Python is a programming language, obviously. It's an interpreted high-level general-purpose programming language, and it's object-oriented, procedural, imperative, functional, structured, reflective. So it has a lot of idioms integrated into the language itself. It's dynamically typed and garbage collected, and it has this battery included philosophy. And the main selling point is more or less it tries to avoid premature optimization by moving time-critical functions to extension modules, which are written in faster languages usually. If you open up Python and type in import this, you will get this Zen of Python, which more or less summarizes how the language is designed on. So the basic principles of the Python language, like beautiful is better than ugly, explicit is better than implicit, etc. Those are fairly good advices. And the popularity of Python has increased a lot in the past. So as you can see, here's a timeline. This is the TYPE Programming Community Index, which tracks the popularity of languages. Python started at a very low rate at the beginning. This is the blue line. And now it's the most popular language according to TYPE Index. So it's even more popular than C or C++. And it's also a very loved language. This is the Stack Overflow survey from 2022, where they did a survey with a lot of people, with a lot of developers. And the Python is at the 6th place, right below Julia, with 67% of love, and the other one is the hate relationship. Okay, so just to be able to adapt my talk a little bit to the audience, I like to do this tiny little game. So I'd like to ask you to raise your hands. Also in the Zoom, I see everybody's hands. So just click on the raise hands button, and I will yeah, almost working. Yeah, it's working. 3 people. So also here, just raise your hands. It will only last like a minute or so. So keep your hands up until you see a question where your answer is no, and then you are out. Okay, so the first question is, have you ever launched a Python interpreter? The second one, have you ever wrote for or while loops or if-else statements? Okay, nice. Everyone's here, your own functions, nice. Classes, okay. List, dict, set comprehensions, okay. Just click on the button in the Zoom if you are not there anymore. Nice. Do you know what a generator is? Okay, I lost everybody here. And have you implemented a decorator? Okay, in the Zoom is like half of the people out. Okay, a meta class, a C extension. And the last question, which usually nobody is able to answer, do you know and can you explain the output of the following line? You have to know it if you're a Python expert. Otherwise, oh, 1 people. One guy, no. All right. Okay, now I know my audience. That's nice. Let's talk about this line because I find it very interesting when it comes to performance in Python. So the question is, what is the output of print? 5 is 7 minus 2, and 300 is 302 minus 2. So if you type it in Python 2.7, you get true and false. which is kind of interesting because first, if we read this, we would think 5 is 5 and 300 is 300. So obviously it's true for 5, but not for 300. And it's kind of weird. Then, of course, times move on. You upgrade your Python, you land at Python 3.6. You get the same answer. It's fine. Then you upgrade your Python, and suddenly it's true, which is still weird, but different from before. In Python 3.8, they added a few warnings just to make sure you are doing something wrong, that you know about it. And then again, 3.9 is also true and true. So this makes little sense. And we want to explore this right now. So how does this work? Or what is happening? If you look at the implementations, you will notice that the current implementation of Python keeps an array of integer objects in the memory when you launch a Python interpreter, so a Python process. And all the integers between -5 and 256 are cached for you. So they are pre-allocated and they are sitting in the memory. And of course, is not the equal operator in this sense. Is means true if X and Y are the same object. So if they are pointing to the same object. And now it makes, of course, sense. Here's, by the way, here you can see the array which stores these small ints. So if you have something like 5 and another 5 during a process, they point all to the same object because it's between this -5 and -256. So this is one of the optimizations Python had to make the language faster because they realize these numbers are used very, very often and it doesn't make sense to allocate them all the time. And in Python 3.7, you notice that the output is suddenly different. They optimized the compiler. They realized that in the single line of code, these values are the same, so it will point to the same object in memory. Okay, so why is Python so popular in science? Is of course one of the first things is its ease of use. So scientists don't know and don't want to program usually, at least in my experience. They just want to get work done, and Python is perfect. It's easy to use. It produces readable code, and we know that source code is more often read than written, so that's also fine. You have this interactive workflow. This means that you can just type in something, hit enter, and get immediate results back, and then you know if you have typed in something stupid or something cool. And of course, there are lots of scientific libraries, and machine learning is everywhere. So it's very tempting to use a language which is easy to use and which comes with all the batteries also included, which is one of the selling points of Python. There are tons of built-in useful supplementary functionality. So part of the standard library of Python just to work with everyday stuff. And of course, it's a general purpose language so that scientists can focus on a single language to rule them all. And of course, I questioned it a little bit, and we will see why. So the next slide shows the performance of languages. I like this graph. This is taken from the Julia page. This shows the execution time of some benchmarks, some little benchmarks. This is not really representative. Of course, you can do it better. But here, basically, in different languages, you have implemented this benchmark with your best knowledge. And here you can see the execution time. So our reference is C, and you can see that Python has a lot of spread in the execution time. And you can also see that something like matrix multiply is almost the same for all the languages because they are using the same C and Fortran libraries behind the scenes like BLAS to do the calculations. Okay, now let's talk about these Python internals to understand why Python is so slow or why these problems are there. First, I would like to mention that Python has no formal specification. This may sound weird. So in contrast to C, or other languages like Julia, etc., you don't have a formal specification like one single implementation, and this is the language. There is simply a Python language reference, which is written in English. So if you go there, it's really just written in English. You can read how objects should look like and how things should be implemented. And there's one implementation which is called the reference implementation, but it's not the only one. So this one is called CPython, and this contains implementation details which are even not part of the language of this language reference. So example, the garbage collector and reference count, though those are not mentioned in the Python language reference. So Python is partly defined by the Python language reference and its main implementation, CPython. And as I said, there are several other implementations like TYPE, JIT-EXAMPLE, which is stuck at Python 2.7. Then we have IronPython, which also supports 2.7 and 3.4, etc. So yeah, these are written in C# and Java, obviously. Okay, so from now on, when I talk when I mention Python, I mean the CPython implementation. Okay, let's see how we get from source to runtime, because this is something which is always a little bit confusing. So as I mentioned at my disclaimer, this is really simplified, but to get a feeling what happens, we start with our source code, which is just a simple function, which we know with the Python syntax. And then we have some compiler magic. So in principle, it's behind the scenes, it's much more complicated. It's a tokenizer, indexer, etc. But this basically produces bytecode. And this is the bytecode which comes out. This consists of some operations and some arguments to these operations. And this is what is interpreted during runtime. So during runtime, you go just one by one through these operations and you interpret these things. And then you get, and this is basically a runtime definition where you get the machine code. So let's get back to our example, which we have seen with this 5 minus 7, 5 is 7 minus 2 and 302 minus 2. If you look at the disassembled code, so Python has a built-in disassembler where you can just give it a function, compile it, and then show the bytecode. You can see that this is the code for Python 3.6 and Python 3.7. If you remember, we have this was the first difference we observed. So one was the true and false answer, and the other had the answer true and true. And the differences are very subtle, but just to show you how it works, we are loading some constants into memory. So there you can see that first load const at position 0 is called, and then load const at position 6 is called. So we are loading two constants from different positions out of this co-const array, namely this 5 and the other 5. And we know that it will still point to the same object. So these are two different places in this array, but they are still pointing to the same object. That's why you get true and true for this particular example. And the 300, they're also sitting at different positions, but they're also pointing to different objects. In Python 3.7, it's different because you can see that it loads the constant from the very same register, from the very same position of the co-const. So it figured out during compilation that this indeed should be the same number. So this has nothing to do with these cache numbers. Okay, here again, where you have to look to sitting at the same places, or so they are also the same objects. Okay, then a nice comment about this stuff. So because I told you Python has to cache these numbers because of performance reasons, now you can think of why isn't it just an integer? Because in Python, everything is an object. And there's this nice little comment in object.h if you open it in the Python source code, and it says an object has a type that determines what it represents and what kind of data it contains. Okay, an object's type is fixed when it's created, and types themselves are represented as objects, and the type itself is a pointer pointing to the object representing to the type, which contains a pointer to itself. So, of course, this goes for trouble if even a number is such a thing, right? And this is basically how it looks like. So if you have data in Python, just an integer, this is then deriving from this PyObject, and it's a PyInt object, which was basically later named to a PyLong ingest because we unified long and int numbers in Python, but it's just a side note. You have this type, you have this reference count, and somewhere you have this value, and then of course you have some other pointers which point to the type itself, etc., and then the type itself points to itself, etc. Okay, so this means that if you work with Python and do something really simple, like array equals and then a list of numbers, one would think that this is just a list of numbers, so 3 integers. But in fact, you have created 4 objects, the list, and 3 numbers. And these 3 numbers have reference counts, the list itself has reference counts, and in Python, this is not an array, it's a list, and it's a double linked list. So each element contains a pointer to the previous element and to the next element. So all this data needs to be somehow stored, and technically the lower limit for the size of this thing is something around 168 bytes. And technically, we only require 24 bytes, so only these 3 numbers which has a type and sit somewhere in the memory. So this is a real inefficient thing. Another thing which is really annoying, your best friend and worst enemy, is the global interpreter lock. This was introduced in Python to get rid of memory issues, like memory leaks and racing conditions. And this prevents you from executing code in parallel. This means that I've shown you this bytecode. This bytecode can only be executed one by one. It's not possible to launch, to execute 2 these bytecode operations at the same time. So as I said, it's a very simple solution to memory safety because Python uses reference counting, and it would be really fatal if you forget to, or if some reference counting mutations were not atomic. And even though Python is real threads, they never execute bytecode at the same time. So this is the result. You have context switching, so you can use threads, but every time you switch the thread, the frame, so-called frame, needs to be transferred to the next thread, and this contains the state, so we don't get lost of our data and pointers. So threads perform really, really badly if you switch between CPU-bound tasks. It does a good job if you mix it with IO-heavy tasks like downloading files, etc. And this is what I would like to show you with a really simple example. Here's a single-threaded application which just counts back from 100 million to 0. And if you time this, you get something like 3 seconds. If you do this with 2 threads, so 2 threads counting from 50 millions back to 0, and compare the times, you see that it takes even longer. So it's not even close to what you expected. We would think that it's, of course, twice as fast or so. And this is what happens. So this is a graphic from David Beasley, who presented it in like in 2010. So it's very old, and it's also based on Python 2.6, but it's still the very same thing in modern Python, Python 3. And you can see how the context is switched. So the program is jumping between the threads. There is no parallel execution at any point. It even gets worse if you use more of them. So, and this is a big overhead. That's why it's slower. Okay, so you may ask, huge overhead, and every single object is big, and there is no parallel execution. How could Python ever compete with all the super fast C and C++ and Fortran software? And the answer to that is extensions and interfaces to fast languages like C and C++, Fortran, etc. Those can also release the GIL and do the heavy stuff in the background. So let's do some dumb speed comparisons. For example, here, 1 million randomly generated numbers. If I calculate the mean with just bare Python functions like this, sum and the length, I get something around 3 milliseconds. If I do the same with an extension module, let's call it an extension module, NumPy, you probably know this. It's already 16 times faster. So here I generated the numbers as an array because that was the easiest to make it, but I timed only this np mean function, which basically iterates through and calculates the mean. So you see it's 16 times faster. And then we have also another tool which is called Numba. If you do this, we can basically reach 3 times performance of the original Python implementation. If you do this in Julia, you are basically at the NumPy range with your stuff. So you don't need to call anything else there. And to show you what's happening here, and we will understand this later, there are some crazy LLVM compiler optimizations. Numba and Julia, for example, are using LLVM compilers. So here's another function called simple sum. So we are summing up numbers from 0 to 100 million. A pure Python implementation just does this for loop, and everyone knows never use a for loop in Python unless you have like 3 elements or so, then it's fine. So if we sum this up, it takes like 3 seconds. If you use NumPy for this with a similar functionality and the same result, it's already like 75 times faster. If you do this with Numba, and Numba is a really magical thing, you just decorate the function, which means that Numba will eat this function and spit out another function, and then it gets called if you call this function with the same type again. So it's very seamless. It's exactly the same implementation as before. I only added 1 line. It's suddenly 34 million times faster. Like, now you're scratching your head, probably. I hope so. If you do this in Julia, it's 150 million times faster. Okay, now all the computer scientists should scratch their heads, like, how is this possible? I have 100 million numbers and 19 nanoseconds, or whatever it is, yeah, 19 nanoseconds. Something is fishy here. Yes, if you look at the code, at the native code, so this is the machine code of the Julia code, you will notice that it is doing some really basic operations and not so many of them, right? So these are really machine codes, so the CPU instructions. And there is some subtraction, another subtraction, a multiplication, then umul h, something like upper 64-bit copying after multiplication, extract, and then add and sub, and then you get the magical result. I tested it, it works. It works for all kinds of, and I tested. Yeah, and the answer to this is LLVM optimized something, namely you may know this formula to calculate the consecutive sum of numbers. And this is basically what's implemented there, a little bit on the fancy way. And of course, that's also the same as Numba does. So we see that Python can be made faster, easily. But there are some caveats. And my next slide calls why we can't have nice things, aka vectorize for your life. So we all know classes, and classes are really fun to structure your code. It makes code easier to understand. It makes code easier to read, and it makes it easier to communicate your designs. So classes and then cleverly designed class hierarchies makes it easier for us also to share our code. And it is very tempting to take this object-oriented thing very seriously and to model all your data in objects and etc. But the problem is the more fine-grained this gets, the bigger is the impact on performance, especially in Python, because of course everything is still an object. And if you do fine-grained stuff, like in this example, imagine a neutrino detector, which consists of PMTs to measure photons. And each triggered signal represented by this hit class, where I only have a few simple primitive data structures. This is already a bloated class in Python. And now imagine you have like a trigger rate of 200 hertz, and each event consists of several thousands of hits. You will likely not want to make a list, a doubly linked list of these hit class instances. It's a very bad idea. You have a lot of memory overhead, and you cannot rework of this. And what you are told to, when you try to work with Python and big data structures, is don't use. Sorry, there is struct of arrays, and there is also this concept of array of structs. And so instead of having an array of hits, which we have seen in the past slide, we basically use a single instance with multiple arrays. So instead of having a class where we instantiate millions of them, we just have one class, and each field consists of these single fields, which are contiguous arrays in memory. So in this case, we see that we can use NumPy for this. We have a structured D type where we tell that there is a PMT ID, which is an unsigned integer 32, then a time, which is a float 64, TOT, time over threshold, which is a uint 8, etc., etc. And when we instantiate it, we can access hits.time, and this will only get the time back. So it basically refers to this field of this thing, and we will get all the times for all the hits. And hits dot, etc., etc. But we can also access it one by one. So that makes it a little bit easier to work with. Okay, and instead of having these array of hits, sorry, this slide is second time. Okay. So yeah, and then of course you cannot write such nice function which you could, for example, do in Julia or C++ or any other high level or lower level language where you can use these types to simply filter your hits for triggered hits. Here I can just simply write a function which loops through all the hits and just grab those which are triggered. In Python, it's much more complicated if you work with this vectorized stuff. So this is where NumPy shines, basically, but with caveats. So NumPy is this fundamental package for scientific computing in Python, and it gives us this powerful n-dimensional object called ndarray. It has these broadcasting functions where you can do operations on slices and combine multiple arrays together. And it also gives you tools to integrate C and C++ and Fortran stuff. And of course, a lot of linear algebra and Fourier stuff and random number capabilities. And of course, most of the scientific libraries are built upon NumPy. So let's look at this ndarray and let's see the difference between this and what we have seen in Python. So if you create an array like this one, it's just a very simple array. It looks like this in the memory, more or less. It's not so colorful, but it's almost the same. It has a type, so it has a valid type, which is the smallest type we can get in this case, or what we specify. If we don't specify anything, it takes int 64, but we can choose the type and it's fixed. So the computer knows that these are sitting next to each other, and it only knows to type once at the beginning of this array. It has a dimension and a shape. So as I said, it's a contiguous array, and now we can do operations on it, and the CPU can just walk through them. It doesn't have to look up in the memory, in the heap or whatever, and jump around to get these values and destruct them. It just knows, okay, the next whatever 100 million entries are int 64, and I can do these operations which are asked for. It's compatible with C and Fortran, so you can pass them between these libraries back and forth. So yeah, I can more or less skip this. We all know this. If you have used NumPy, you can multiply things, etc. Everything works in the background. So It's very natural to use them, and reshaping is a feature where you can see that it's really effectively working in the background. Here we have an array, and if we want to reshape it, we don't need to copy things around or whatever. What NumPy does, if you call the reshape and the new shape of this object to make, for example, a matrix out of this array, is it sets the iterator limits internally, just to other numbers. So this is really fast, and then it feels like it's something which is two-dimensional suddenly. You can see it also here. If you have like 10 million elements, and I reshape it to the matrix of the dimensions 100 times 5,000 times 20. It only takes like 130 nanoseconds, which is just a handful of operations on the CPU. Okay, all fine. NumPy to rule them all? Unfortunately not. And this is one of the things where people hit the wall really quickly. There are a lot of hidden allocations. Here's an example program. There is a small function called peak memory usage. This will just spit out the maximum memory the program used during the runtime, the process. And the main function is really simple. It defines n to be 1 million, and then I instantiate a variable called a with the n random numbers. Then I instantiate another one with another 1 million numbers, and then I do this operation c equals 2 times a plus 3 times b. So very simple. Everyone does this with much more complicated stuff. And this is what I get. So I print out the peak memory usage after each operation here. And you can see that after all the libraries are loaded, we occupy 28 megabytes in memory. After A is allocated, we get 36 megabytes, so 8 megabytes plus. That makes sense because float 64 has 8 bytes, and we have 1 million of them, so 8 megabytes. After B is allocated, we allocate another 8 megabytes. That makes also sense. But to calculate C, the peak memory usage suddenly goes up to 67. And this is, of course, weird, but if you look at the code, it's fairly obvious. If you execute this, Python has no knowledge about what happens here. So the first multiplication will create a temporary array. So this will basically go through A. It will allocate another array with the same content, and then but multiplied by 2. Right after that, because we don't have any parallel execution, 3 times B is allocated and calculated. And then at the very end, the green line is the plus operation. This will allocate another array, which will be then kept and assigned to C. So beware that this peak might kill your job on an HPC computer if you're using like gigabytes or whatever to calculate things. This happens especially a lot with Pandas, because all these join and concat operations, etc., do basically the same thing. So there are some things which you can use. Here's the very same functionality again, but I reused A and B, so already allocated stuff in memory to calculate these numbers. And here you can see that A is allocated, B is allocated, so 8, 8. And after I calculate 2 times A with a trick, by using A and B with the out parameter to the NumPy add function, multiply function, I don't get any new allocations, so that's good. We are reusing the memory. Of course, this has a caveat because we now have mutated A and B, but we have a lowest memory footprint we can get. So as an example again, instead of doing A equals A plus B, you can do np.add A, B, and then out A, which means use the buffer A as output. Yes, sure.
Yeah. What is easy about that? Nothing.
That's not easy.
To replace something obvious with some weird syntax. A lot of shit is happening behind the scenes. All this is unrelated to what I want to do.
Yes,
so
exactly.
I think people that this is easy. It's beyond my imagination.
Yeah. So the question is, why do people think that this is easy? I don't think that this is easy. I also never said that this is easy. I only said that you can do this to solve the problem we had in the slide before. So these are the downsides of using NumPy for this stuff. And let me just go further in my presentation. We will get to this later. So this is a solution. It's not easy. You have to know this. But let me quickly recap. So memory and performance issues. So your code may work for small examples, but may escalate quickly with peak memory usage if you don't handle things with care. So users can blindly perform chains of transformations and then but this will also trigger redundant loops. So what I have not told you yet is it uses more memory, but it also loops every time. So if you calculate something like 2 times A plus 3 times B, it will go multiple times over these arrays because it has to. Python is not able to know this when you write the syntax out. So yeah, all this unnecessary stuff. And the masking and slicing is also the root of all evil, because this happens a lot if you use NumPy or Pandas or other stuff. Namely, masks are used to cut data, to reduce your data to a sensible size. For example, I showed you this thing with millions of hits per event, and then we have, of course, large events. We have really large files where we want to process them. If we would do this in Python and do some cuts, because we're only interested in hits which have like a higher time over threshold than 23 nanoseconds, etc., and lie between a specific time, etc. So these all will allocate temporary arrays with the same size as hits. So we need to make here 4 allocations, 4 loops, and then again we need to concatenate them. We need to apply this binary add operation 3 times. So we are creating like 7 temporary arrays, and this, if the garbage collector is not fast enough, these will live at exactly the same time, or just exactly the same time, and occupy a lot of memory. Okay, so you need to write your code so that it iterates through a configurable size of chunks. This is very important in Python. So, for example, loop through X events, and X is your configurable thing, instead of file by file. Your test file might be small, but when you are processing your experiments data, they might give you a file which is like 10 times larger, and this will occupy maybe 10 times more memory, or even 10 to the power of 2 times the memory, etc., depending on how you did that. So let's talk about NUMEXPR. This is also a solution to something, make it easier. We had this problem with these multiple allocations and multiple iterations. And this is where NUMEXPR was invented. So this is yet another invention to make Python fit scientific programming or scientific computing. You can see I imported NumPy and NUMEXPR. I created some arrays, and now I can just call NE, evaluate, and give it a string. And this string is then parsed and passed to a virtual machine. So this is really funny, because it gives you the correct result. And what it does is basically it knows that, okay, you want to allocate, you want to calculate A to the power of 2 and 3 times B. And it will only loop once over the whole thing and allocate just the right size of things. So there's, of course, also a speed up if you take it to the next level. Like here, I have a lot of extra allocations. This runs in 82 milliseconds, and here in NUMEXPR, I also activated 4 threads just to show you that you can easily create parallel computations. When I run the same thing, it's like 10 times faster or so. Of course, running on 4 threads, so don't take it as granted, but it's faster. And most importantly, it has a minimal memory footprint. And it has a lot of supported operators, so you can do this string virtual machine translation. You can pass in a lot of operators like these, and a lot of functions. So it even supports things like complex numbers, etc., etc. And if I come back to the example, you can see that indeed this program is now. So I only switched this line compared to the very first example. Now it's doing this NE evaluate 2 times A plus 3 times B, and we don't get any extra allocations. Another library which is there to solve your problems with weirdly shaped data is AWKARD array. This is a very helpful library in high energy physics, for example, where we have awkwardly structured data. Like we have an array or a vector of events, and each event has different number of hits, and each hit has different number of attributes or whatever. So this was designed to make this limitation of NumPy arrays, namely that they are rectangular, to variable length structures which are nested or doubly nested, etc. It's like tree-like, and it has a lot of speed and performance optimizations behind the scenes. So you can use it just like NumPy, but with awkwardly structured data. It's written in Python and C++, and here you can see an example where I instantiate a list with different number of other sub-lists. You cannot do this in Python with NumPy, because it would basically give you an object array back, and then you have just Python objects. And here you can see that it has a definite type. The type says 3 times var times int64, which means that it contains 3 elements of variable length of int64s. And you can do this magic slicing like this column means from all the elements, give me the first item. So it knows that it has to iterate through all these sub arrays, and it will only give you the first element of that. So you can look at the first track in your events or whatever. Okay, so all kinds of multiply nested structures, and it's type stable, and it has fancy indexing and all the stuff. So it feels like Pandas, but with awkwardly jagged arrays. So if you work with these awkwardly jagged stuff, you should watch this presentation where Jim Pivarsky, the main author, he's a very nice guy, by the way. He shows these wonderful demonstrations how to work with that. Okay, so, and when things are getting more complicated than 2 times A plus 3 times P, because the world is just much more complicated than this, unfortunately, we have things like Numba. This is the JIT LLVM compiler for Python. And what it does is it's basically a compiler which tries to speed up numerical calculations without introducing any fancy syntax or whatever into your Python code, just a decorator to decorator functions, which are then LLVM compiled. So it uses LLVM to boil down the Python code to JIT optimized machine code. And yeah, it will only execute functions which you decorated yourself, and it has a very limited feature set of functions, so you have to be careful there. But it can generate native code for CPU and GPU, and it integrates very well with scientific software stack like NumPy, etc. So you can use it, run it side by side with regular Python code, and also these third-party applications, and it has CUDA support and core scalability by releasing also the GIL. Yeah, so you can even create NumPy ufuncs for all the experts out there. Okay, as I said, limited support for data structures, so don't take this as the solution for everything. Unfortunately, there are a lot of caveats there. You cannot use your class instances. Most of the time, nothing will work. Just if you write bare for loops, it will work, and this is where we use it. So from source to runtime, here's what we know. The difference is Numba hooks into the interpreter. So basically, it acts on this bytecode, and it does some control flow graphs, data flow graphs, bytecode interpretation. It creates the Numba intermediate representation. It does some type inference, so it tries to guess the types of the stuff and also to fix them. This is of course very complicated in Python because it's dynamically typed. But then it creates this type Numba intermediate representation, which is then lowered to the LLVM intermediate representation, and then we have the compiled code with CodeGen via LLVM. So a quick example, a 2D sum, which we don't have in native Python, but we implemented it. If you just put NBJIT at the top, we get a speed up of like a factor of 135 or so. And we can also vectorize stuff for the experts out there. We can also parallelize things, but I will not get into this. Okay, so Python is your everyday hammer, but the problem is that if you are holding a hammer, everything looks like a nail. And this is more or less the biggest problem with Python in science. You need to choose your tools with care. So Python is a powerful language, and it can be used for many, many different tasks, but it's really easy to write horrible code performance. And it's even easier to write code which simply does not scale. So there are a lot of tools out there which I cannot cover in this talk, but they can make your life easier. But again, the problem is, contrary to Python's expressiveness, high-performance code is often neither nicely readable nor easily maintainable. This is really a problem because people start to write Python programs and then they realize they hit the limits and they need to add even more technology to that, and then the technology stack gets bigger and bigger. And we are also often forced to use high-level Python APIs, which can be very useful, but they act as a barrier. So you often just can call a function which calls some C or Fortran stuff, but you're not able to modify the function of this stuff. You really then need to compile your low-level code, etc. That's what I mean with barrier. And also, you have to be more than a Python expert to write high-performance Python code, which is really silly. But yeah, so yeah, keep all this in mind, and keep also Julia Go for scientific computing. In Julia, you can also call your Python code if you want. So it's the other way around, which is really funny. And yeah, a personal remark, because I'm a Julia lover. I'm a big fan of Julia for science. So it's a language written for scientific computing, and it feels like Python and runs like C. So you don't have to fear for writing for loops, and you can define your own types, your own type hierarchy, etc. It's very expressive. It's interactive for prototyping, just like Python with REPL. Naively written code is often very close to optimal performance, and it also runs in Jupyter notebooks. The Ju stands for Julia, by the way, if you have not known yet. And easy package management, reproducible stuff. So everything is there what you need for science. It's not like Python, which we made to patch it to make it work for our daily scientific work, but it's also there. Yeah. So this is how it looks like. Different editors there. You may recognize Jupyter. There's Emacs, there's VS Code, etc. And I find it also funny if you go to the Julia packages library, you don't find categories like web servers or whatever. You find something like graph theory and sparse matrices, etc. So these are the categories there. The packages are really powerful there. And yeah. And last but not least, with great power comes great responsibility from Uncle Ben. You may remember him from Spider-Man. I would like to spend a final word on green computing and green coding. I think this is really, really important because in HPC, we can easily waste energy with inefficient code. And I spent a lot of time in the past like 10 years optimizing Python code, and students were coming to me and asking me why it takes so long to calculate, etc. And after a long and exhaustive iterations, we figured out that it can be run like hundreds or even 1,000 times faster. And of course, it's very sad to know that these people already wasted like 10,000s or 100,000s of CPU hours. So yeah, it's just a matter of few keystrokes to launch thousands of computing jobs and waste energy. So it's also your responsibility to learn how to use these resources efficiently and with care. And that's why this talk is aiming for these Python internals to know what's happening there. And here are some examples. This is from an energy efficiency across programming languages paper, which was released a few years ago. You can see that Python is at the very, very end. So we really need to learn how to utilize high performance stuff if you want to work with Python. And in contrast to these benchmark games thing, which you may know, they benchmark a lot of different languages, I think 27 or so with many, many implementations. And there you can see that at the first the top places, you almost always find something like Rust or C or Julia, etc. So keep this in mind.
Just a comment here. I firmly believe that all these are random numbers.
Okay.
Can talk later.
Okay, we can talk later. Sure. Okay,
I
yeah.
think there's a raised hand from the group.
Yes, that's also my last slide, so we can switch locations.
Take a look.
Many thanks.
All right. Thanks a lot for this wonderful talk.